Welcome to a new and critical section on data handling, using Pydantic for data validation. In modern Python applications, data comes from external sources like APIs, JSON files, or forms. Ensuring this data is accurate and fits a predefined structure is paramount. Pydantic is the leading library for achieving robust data validation and settings management. 1. The need for data validation. When you receive data, say a user registration form, you must ensure the age is an integer, the email is a valid format, and the name is present. Without validation, incorrect data can crash your application or corrupt your database. Pydantic automatically performs these checks when data is loaded into a Pydantic model. 2. What is Pydantic? Pydantic is a library that uses Python type annotations to enforce data shape. It offers runtime type checking, meaning it validates the data when you create an object, not just when you define the class. It automatically converts data types where possible, like turning the string 10 into the integer 10, and raises clear errors when validation fails. 3. Pydantic models and type hinting. The foundation of Pydantic is the model, which is a class that inherits from base model. Inside this class, we define fields using standard Python type hints, str, int, bool, and so on. This simple definition tells Pydantic exactly what structure the data must have and what types are expected. Pydantic then enforces these types automatically. To summarize, Pydantic makes data validation clean and Pythonic. Our next lecture 42.02, Setup Project. See you there. Welcome back. To begin using Pydantic, we first need to set up our development environment. This lecture covers the simple installation process using pip3 and establishes the basic Python file structure we will use throughout this section. 1. Installing Pydantic. Pydantic is a third-party library, so we must install it using pip3. Open your terminal or command prompt and run pip3 install Pydantic. This command installs the core Pydantic library and its dependencies, making it available for use in your Python projects. 2. Setting up the project file. For our exercises, create a new Python file, perhaps called data_validation.py. The first step in any Pydantic script is importing the base model class, which is the foundation of all Pydantic data structures. We will then define our data models by inheriting from base model. 3. Pydantic's dependence on type hinting. Remember that Pydantic relies completely on Python's type hinting syntax. When defining fields in our models, we will rigorously use standard types like str, int, and float, as well as types from the built-in typing module, such as list and dict. A strong understanding of Python type hinting is key to using Pydantic effectively. To summarize, we are ready to define and test our first model. Our next lecture 42.03, Pydantic in action. See you there. Welcome back. Now that Pydantic is installed, let's see it in action. We will define a simple data model and test how Pydantic handles various types of input, focusing on two key behaviors: successful validation and automatic type coercion, and failure handling. 1. Defining the sensor reading model. We define a simple model that inherits from base model. It requires an integer ID, a floating point temperature, and a string status. Remember, by simply using type hints, we are defining our required data structure and validation rules. Two, successful validation and coercion. First, we test with data that perfectly matches the types. This works instantly. Next, we test with data that requires type coercion. We pass strings where integers and floats are expected. Pydantic is smart. It sees 102, can be converted to an integer, and 25, can be converted to a float. It performs these conversions automatically, and the resulting Pydantic object holds the correct native Python types. Three, handling invalid data. If the input data is missing a required field, or if the type cannot be coerced, Pydantic raises a validation error. This error contains a clear list of all fields that failed validation and why. This is incredibly valuable because it tells you exactly what data to fix. We must always wrap Pydantic instantiation in a try except block to safely handle external, potentially invalid data. To summarize, Pydantic ensures data integrity at the entry point of your application. Our next lecture 42.04. Use optional. See you there. Welcome back. In the real world, data is rarely perfectly complete. Sometimes a field might be missing, but we still want the rest of the data to validate. In this lecture, we learn how to define optional fields in Pydantic models using the optional type, which allows a field to be present or safely omitted. 1. Defining optional fields. To make a field optional, we use the optional type, which must be imported from the typing module. Optional of string means the field can contain a string or it can be none. By setting an explicit default value, like equals na, we tell Pydantic that the field is not strictly required during initialization. Similarly, if we set a default value like equals false for is underscore premia, the field automatically becomes optional with that default value. Two, using the optional union syntax. For those using Python 3.10 or newer, there is a cleaner way to define optional types using the pipe or union operator. Float pipe none means the field can be either a float or none. This is the preferred modern syntax and is functionally identical to optional of float. 3. Testing with missing fields. When we instantiate the customer model with only customer underscore ID, Pydantic successfully creates the object because the other two fields are optional. The phone underscore number defaults to none, and is underscore premium defaults to false. If we were to omit customer underscore ID, the model would fail validation, as it is a required field with no default value. To summarize, optional fields are essential for handling flexible or incomplete data structures. Our next lecture 42.05. Use constraints. See you there. Welcome back. Pydantic's power goes beyond simple type checking. In this lecture, we explore how to enforce specific constraints on values, such as ensuring an integer falls within a certain range or a string has a minimum length. This is achieved using Pydantic's built-in constraint types. 1. Constrained integer, conint. To ensure an integer field, like a rating, is within a specific boundary, we use conint. By setting gt equals 0 and le equals 10, we ensure the score must be greater than 0 and less than or equal to 10. If a number outside this range is provided, Pydantic immediately raises a validation error. 2. Constrained string, constr. For strings, the constr utility allows us to enforce rules like minimum and maximum length. Here, we set a min underscore length of 3. We also add strip underscore whitespace equals true, a powerful feature that cleans the string before validation, preventing users from submitting strings that are just spaces. 3. Testing constraints. We first confirm that valid data, like a score of 7, passes instantly. Then we test the boundaries. When we try to instantiate rating with a score of 11, Pydantic immediately checks the conint constraints, finds that it is not less than or equal to 10, and raises a precise validation error. Similarly, attempting to use a username that is too short triggers the constr error. To summarize, constraint types are vital for ensuring the quality of your data. Our next lecture 42.06, a commerce example. See you there. Welcome to the final lecture in our Pydantic section. We have covered models, optional fields, and constraints. Now, we will bring these concepts together to build a robust e-commerce product data model, simulating real-world data validation challenges. 1. Defining the e-commerce model. Our product model defines 4 fields, each with different validation rules. We use conint to limit the product underscore ID to a sensible range. We use confloat to ensure the price is always greater than 0. The description is optional, defaulting to none. Finally, tags must be a list of strings. Two. Successful validation. We test with data that omits the optional description and provides the product underscore ID as a string. Pydantic successfully coerces the ID to an integer and validates that the price is positive, creating the product1 object without errors. 3. Handling multiple validation failures. Now we deliberately pass bad data. The ID is too large, the price is negative, and the required tags list is missing. When the validation error is raised, Pydantic strength is apparent. It aggregates all the failures into one detailed error list, showing which field failed, lock, and the specific reason, message, for each failure. This is extremely helpful for debugging and informing users or external APIs about data problems. To summarize, Pydantic is your shield against bad data, ensuring robust application logic. This concludes our section on Pydantic. Our next section is Wrap Up, starting with Lecture 43.01. Congratulations and thank you. See you there.